I'm going to go ahead and get started. So this week we're focused on two different types of analysis, really looking at whether or not a relationship exists between two different sets of data. And so there are a few different ways that we can do this. The first one is chi-square. And what chi-square is looking at is whether or not there's a significant difference between any two populations. When we reject a hypothesis, we're basically stating that there was no significant difference, and any difference we do see is due to sampling error or data error. So we deal with two types of hypothesis. The null hypothesis typically is misunderstood as meaning no relationship. But really what the null hypothesis means doesn't necessarily mean zero, it means nullify. It's the statement that we're trying to refute or argue with our data. The p-value, which we'll get into here in just a little bit, the p-value is usually 0.05. That's the standard test for independence unless you're given another value in one of your problems. 0.05 means that we can say with 95% confidence level that our hypothesis is either rejected or not rejected. So a p-value that's greater than 0.05 would say the variables are independent or not linked together. A p-value of less than 0.05 would state that there's some sort of relationship or connection between the variables, whether it's an inverse relationship or a direct relationship. So in this problem, which is at 1217, we're looking at whether or not there's a relationship between sleeping on the job and job category. So our null hypothesis is that sleeping on the job is independent of job category. That's what we're trying to refute. So the alternative hypothesis would be that sleeping on the job is dependent on job category, meaning that a government professional might be more likely to fall asleep on the job, or an IT professional might be more likely to fall asleep on the job. So we actually take our data table and we copy it 3 times. Or we copy it 2 more times, and we start with our actual data. So this is the data that was actually provided in the problem. And the first thing we're going to do is total all the yeses and all the nos, and then get a total of the total number of people surveyed. Then we're going to take a look at, of these proportions of the total, what would be our expected value for each job category, yes and no. So we take our total for the yeses and we multiply it by our total for the IT professional and divide it by the total number of people surveyed. And we don't want to lock these down because in this one, we're going to take our total for our yeses multiplied by our total for government professional and divided it by our total number of surveys. So we'll continue to do that for each of these boxes. The total of our IT professional multiplied by the total of the no's and divided by our total number surveyed. Then we'll take a look at our chi-square. And the chi-square formula is our actual minus our expected to the power of 2 divided by our expected. So we can enter that into Excel as our actual minus our expected to the power of 2 divided by our expected. And that gives us the ability to calculate our chi-square statistic, which is just the sum of all of our chi-square data. So we just equal sum and then parentheses, and we're going to highlight all 4 boxes and end our parentheses. Our degrees of freedom is equal to our number of rows minus 1. So in this case, we have 2 rows, so we subtract 1, and our degrees of freedom is 1. Our critical value then is a little bit more challenging. We actually use the formula chi-square, so CHISQ.INV.RT. And then we enter in our probability. So in this particular problem, it wants to know what a 99% confidence level would be. So we're going to enter in a p-value of 0.01. And then our degrees of freedom. And I just highlighted our degrees of freedom so that if that were to change for something, that we will have this already selected. And then the next thing that we're going to take is this p-value. So our p-value, we can use the chi-square or CHISQ.DIST.RT function in Excel. And the first thing it's going to ask is our x, which is our chi-square statistic, and then again our degrees of freedom. We can also accomplish the same thing by using the chi-square test formula, which is CHISQ.test, and then we're going to highlight our actual range and our expected range. And you can see that both come up with the same answer. But because our p-value is less than 0.005, we reject our null hypothesis in this case. So our null hypothesis was that sleeping on the job is independent of job category, which means that we accept our alternative hypothesis that sleeping on the job is dependent on job category. So let's take a look at one more of this. We have a couple of different, a little bit more data in this one. In this one, we're taking a look at whether or not there is a quality and source of shipment are independent. So in other words, of the 3 vendors that we have, is quality dependent on the vendor, or is there an independent relationship? So do we have more defective parts coming from one particular vendor? And in this case, we do the same thing. We take our total multiplied by our total for that vendor multiplied by the total defective and divided by the total number of actual data points. And we do the same thing for our chi-square test, and the same for our chi-square statistic. Because we have 3 rows now, our degrees of freedom is 2. And we use this critical value formula. If our test statistic is greater than, we reject our null hypothesis if our test statistic is greater than our critical value. In this case, it's not. So we actually accept our null hypothesis and state that quality and source of the shipment are independent. In other words, it's not a vendor issue. And again, we're using the same types of formulas here for 1221. So you can ultimately use this table here from this one and add rows or copy the tab over and enter in the new data for the different problems. And again for 1242. So we'll get into a different type. This is 14.7 and 14.10 actually dive into correlation. Correlation is looking at whether or not something moves at the same time or in the same direction as something else. or if we can say that there's a relationship there. So in this case, we're looking at, does the number of rainy days affect the number, or is there a relationship of number of shootings and number of rainy days? So does number of rainy days going down mean also correlate with the number of shootings going down and vice versa? Or is there an inverse correlation, meaning when the number of rainy days go down, we see the number of shootings go up? Correlation is different than causation. Causation would be saying that one thing causes another. So the number of rainy days and the increased water collecting in the pool. One is causing the other. In this case, we're just seeing if there's a relationship between one or the other and not looking at causation necessarily. So we can take a look at this formula here for covariance. And we're going to use our covariance and highlight our number of rainy days and then highlight our number of shootings. And then we're going to take a look at our correlation statistic, same thing, and our degrees of freedom. Now, ultimately, what we're doing for degrees of freedom in this one is we're taking our number of rows minus our number of columns, which is why there's a degree of freedom of 3. And then we pull up we use our test statistic formula, and I included the formula here. We can do square roots in Excel using SQRT. When we use the square root formula, or when we identify our t-statistic, we can then look at our chart to determine whether or not our p-value is going to be greater than 0.05. If it is greater than 0.05, we cannot reject the null hypothesis, meaning that the data does not support a correlation. So let's take a look at our chart. We have a test statistic of negative 0.98 and degrees of freedom of 3. So we're going to flip over to this table, and this is provided in your textbooks as well. So we want to know if A is 0.05, so if our p-value is 0.05 and our degrees of freedom is 3, then our test statistic would need to be 2.353. But if we look, our test statistic is negative 0.98. And so in order to get negative, we know that our p-value has to be greater than 0.20. It's off the chart greater than 0.20. So 0.20 is certainly higher than 0.05. So when we go back to our Excel, we can say that p is greater than 0.20 at a 95% confidence level. And since p is greater than 0.05, we cannot reject the null hypothesis. The data does not support a negative correlation. And we can do the same thing here with this particular one, and I'll have you disregard this. In fact, we'll hide this. We'll go into some of that next week. So when we're looking at age versus happiness, our degrees of freedom, again, is going to be 22, because if we do a count, we see that we have 24 rows and we have 2 columns, so our degrees of freedom is 22. We use the same correlation formula and the same test formula. So if we want to know that at the 99% confidence level, our A is going to be 0.01. And so we need to look up what the test statistic is at 3.26. So we're going to flip back here, And with 22 degrees of freedom, our test statistic is now all the way over to the right of the chart. So we know that our p-value is going to be less than 0.005, which is less than our 0.01. So we can say with 99% confidence that we can reject the null hypothesis because our p-value is less than 0.01. And you see here I actually have the correct p-value is 0.003, which of course is less than 0.005, which is as far as the chart goes. And going into next week, we'll identify how to get that p-value using Excel. But for these two problems, you just need to know that the p-value is going to be less than 0.01. By using that chart, you can identify where that p-value is going to sit. So hopefully this will help you get through some of these problems, and if you have any questions, as always, let me know.